Alright, silly people, here's the situation. It's a particle in a magnetic field. It's a spin 1/2 particle specifically. Um, and just to make it more complicated, we're also in a rotating reference frame. Um, and we are meant to pretty much find the expectation value of um, the magnetic moment in the z direction from scratch, starting from these two equations, which I've written here. First of all, um, we're gonna rewrite the second equation um, as being this. So I just moved the rotation operator to the other side of the equation, like that. And then tack on a time derivative to both sides. SZ over h bar psi r is equal to I h bar time derivative of psi. Now, right hand side we know from the first equation is just the Hamiltonian times the time dependent wave function. But we're going to have to do some stuff to the left hand side. So left hand side is going to read, I'm not going to factor the IH bar through yet, we're just going to take derivatives. So we'll have first times the derivative of the second, so d dt psi r plus second times derivative of the first. So I omega sz over h bar exp I omega t sz over h bar times psi r. And on the right hand side it's the Hamiltonian acting on psi. Now we can factor out the exponent, and we can factor through the IH bar. To get IH bar d dt psi r minus omega sz psi r. Yep. On the right hand side, we're going to go ahead and expand the Hamiltonian, which we know from the problem statement is gamma, which is the electromagnetic factor, times the spin vector times the magnetic field vector. And by definition, it's a rotation of the wave function, non-rotating wave function. So we can turn it into minus rotation, a reverse rotation, if you will, of the rotated wave function. That way all of our cats on either side of the equation are the same. So let's move this rotation to the other side now. So on the left hand side we'll just have IH bar d dt. This is pretty much an operator now, minus omega sz times ket psi r. And now that's equal to this rotator operator guy, s dot b. There's a minus gamma here somewhere, yeah. Minus gamma. S dot v. The other rotation operator acting on psi r. Awesome. Now, on the right hand side, we happen to have a form for the magnetic field, which is it's going to be defined as being b cosine omega t in the x hat direction. Let me just do it in this notation. B cosine omega t in the x hat direction minus b sine omega t in the y hat direction, and just b naught in the z hat direction. So s dot b then, we can expand it, and so I'm just going to write the left-hand side of the equation out again for posterity, and then expand the left-hand side, which is now going to be minus gamma exb minus I omega t s z over h bar. And s dot b now is going to be written as sx b cosine omega t minus b sy sine omega t plus b naught sz. And then you're still got this rotator. Why is that not working? Sz over h bar, and all of that has to be acting on the state psi. Got a little gross at the end there, but yeah, acting on state psi r. So we're not going to expand the whole thing into matrix notation, but we are going to expand part of it. First of all, just noting that the rotation operator I omega t s z over h bar just times the third component of the dot product, so b naught s z I omega t s z over h bar. B naught is a constant, and sz will commute with itself, and so this is actually just equal to b naught sz. It doesn't change. So that means that really on the left-hand side of the equation, again, I'm going to write it again for posterity, d dt minus omega sz psi r is going to be, on the right-hand side, minus gamma szb naught. We pulled out the szb naught stuff, but we're still going to have this stuff, which both of the stuff inside the parentheses had a factor of b on there. So it's just the spin operators multiplied by trig functions there. And then the rotator, sz, all of that acting on psi r. Fantastic. Now it's worth turning everything into, you know, okay. Now it's worth noting that the zero frequency, omega naught, is defined as being gamma b naught, which is what we have tacked onto our spin operator sz. So we can rewrite both the left hand and right side of the equation now, where we're just going to leave the IH bar time derivative of ket on the left side, and on the right hand side we're going to move the sz omega over, so we're just going to have sc omega minus omega naught ket psi r, and then all the stuff that we did before, which at this point it is worth changing our spin operators into Pauli matrices. So you're going to have an h bar over 2 here. Sigma x cosine omega t minus sigma y sine omega t. And then the operator is now sigma z over 2 instead of s z over h bar. All of that acting on psi r. Cool. So not even expanding the I'm not going to write the left hand side anymore. Rewriting now the sz stuff, so it's h bar over 2 times the Pauli matrix sigma z times the omega minus omega naught psi r, and then simplifying the prefactor on this guy, which isn't b naught but b, so gamma b h bar over 2, and then this is cosine omega t over 2. So I changed the rotation exponent into the cosine omega t minus sine omega t formulation because it makes it a little bit easier to look at. So it's not an exponent anymore, that's just a rotation operator identity. This stuff remained the same, sine omega t, and then this stuff, the other one of these rotation exponents gets turned into this guy plus now I sigma z sine omega t over 2. All of that multiplied by psi r. Okay. So now let's look at actually turning all of these into matrix notation. That way we can actually do some operations. So we have h bar sigma z over 2 omega minus omega naught psi r, and then now this is minus gamma b h bar over 2, and we're going to start putting everything in matrix notation. So first matrix is going to be cosine omega t over 2 minus I sine omega t over 2, 0, this is 0, this is cosine omega t over 2 plus I sine omega t over 2. The second matrix is a superposition of Pauli x and Pauli y. So no diagonal terms, just the off diagonal ones. So we'll have cosine omega t minus I sine omega t. We'll have cosine omega t plus I sine omega t, 0. And all of that is being multiplied by now the other rotator gets turned into this matrix omega t over 2, 0 cosine omega t over 2 minus I sine omega t over 2, 0 times psi r. Now we're going to notice that everything is multiplied by a factor of h bar. So we're going to divide by h bar on both sides. And we're also going to multiply everything by 2 because everything's divided by 2. Except for the left-hand side, which is now going to read 2I times the time derivative psi r. Right-hand side, we still have this sigma z times omega minus omega naught acting on ket psi r. And we can expand, actually don't expand. First of all, we're going to multiply the first 2 matrices together, which is going to read the diagonal terms. You'll have the cosine omega t gross over 2 plus I sine omega t over 2 stuff multiplied with cosine omega t minus I sine omega t. And then this stuff was cosine omega t over 2 minus I sine omega t over 2 times cosine omega t plus I sine omega t. All of that, again, times the last of these rotation matrices, which I've already written down on the last line, which look like that. Still just acting on psi r. Right. Finally, we can turn all of this into one stupid looking matrix of being 2I d dt psi r is equal to sigma z omega naught minus, or omega minus omega naught psi r. If my handwriting is bad and you don't like it and you're still here, thank you for your patience. Minus gamma b, and then this is one big stupid looking matrix where it's 0. We have cosine omega t over 2. We have plus I sine omega t over 2. We have cosine omega t minus I gross minus I sine omega t. We have cosine omega t over 2 plus I sine omega t over 2. That's the first off-diagonal term. The other off-diagonal term is cosine omega t over 2 minus I sine omega t over 2 times cosine omega t plus I sine omega t. And then times cosine omega t over 2 plus I sine omega t over 2. And actually, that's not a plus, that's a minus. All right. And then the other diagonal term was 0. And that's multiplied by psi r. So we're going to just calculate some polynomials first of all. So we have that cosine omega t over 2 minus I sine omega over 2 is being multiplied by itself in the first off-diagonal term. So we have that that's going to be cosine squared omega t over 2 minus sine squared omega t over 2 minus 2I cosine omega t over 2 sine omega t over 2. And yeesh. Okay. That is a trig identity. That turns into just cosine omega t. That is a trig identity. That just turns into cosine, or I sine minus I sine omega t. Okay, and then on the other um, one of our lovely off diagonal terms, we have a plus sign on our I, and we're squaring it. And that's going to be cosine squared omega t over 2 plus sine squared omega. No, it's still minus. It's still minus. Haha. Over t over 2. But we have a plus sign on the cross term. Cosine omega t over 2 sine omega t over 2. And we're going to use the same trig identities. This is going to be cosine omega t, and this is going to be plus I sine omega t. Cool. So we effectively simplified our little matrix here as being minus gamma b 0, and then we have on this off diagonal we have cosine omega t plus I sine omega t times cosine omega t minus I sine omega t, and then like the same thing that we have down there. And then the diagonal term is 0. Funnily enough, this evaluates to 1. This evaluates to 1. So we've rewritten now our Schrodinger equation as being 2i ddt psi r equals sigma z omega minus omega naught psi r minus gamma b, and then 0, 1, 1, 0 is just sigma x. And that's acting on psi r. And that's pretty much your Schrodinger equation. If you would really like to, you can divide by 2 and multiply by h bar again to make it look a little bit cooler. So I h bar psi, time derivative psi r will be, if you divide by 2 multiplied by h bar, you'd get your spin matrices back. So you get sz omega minus omega naught minus gamma b s x, and that is acting on psi r. And you can treat this as being your Hamiltonian for this situation here. Cool. Now that we have our Hamiltonian, we need to check that our expectation value for the spin is still going to be okay. So what that is saying is we need to look at psi r 0 h psi r 0 and check that we get h bar omega over 2. So expanding our Hamiltonian into matrix notation and writing our initial state in column vector notation, we have this stuff minus gamma b minus omega plus omega naught, initial state h bar over 2, which is just h bar over 2 times the row vector times omega minus omega naught, and then minus gamma b, and so it's just h bar over 2 omega minus omega naught, which does match the classically expected value, because remember we're in a rotating reference frame where omega represents the reference frame. So omega minus omega naught can be thought of as like the total angular velocity. So we find that the expectation value for spin or energy actually, is still h bar omega over 2. So good stuff there. But now we have another thing, and that is we have to determine psi of t from the Schrodinger equation, and put it in the form that Shankar wants. Right. So you can write your Schrodinger equation again. Nothing too crazy here. We have d dt psi r equals h psi r. And we know for a fact that psi r is going to be in the, what is this, the Schrodinger picture? I don't know. It's one of those pictures. It's not Heisenberg, though. Where we have a propagator, u of r of t, acting on the initial state, psi r of 0. Will give you the time-dependent wave equation, psi r, where we can pretty much call our propagator being e to the minus I Hamiltonian t. And notice that if we rewrite the time-dependent thingamajigger, the rotation matrix actually has time dependence in it. So psi r of 0 being psi of 0 multiplied by the rotator, we have e to the 0, so it's just the same thing as the initial state, psi of 0, which is 1, 0 in column vector notation. So we have that psi r is equal to exp minus I omega t sc or h bar. That's just the definition of the rotation. So we can say that the rotator acting on the time-dependent state is equal to the propagator multiplied by the rotator acting on the initial state, which just means that the initial state is now just haha. Okay. That means we can write psi, the time-dependent state that we're looking for, as being the reverse rotator, so we're rotating back into the lab frame, multiplied by our e to the Hamiltonian, so my omega minus omega naught s z minus gamma b s x, operating on the initial state 1, 0. And to get to the form that Shankar prescribed, the way that I found to do it is to change over your e to the Hamiltonian stuff into a rotation matrix, or a rotation operator pretty much, which is defined usually like that. In this case, we find that theta is omega r times t, and we find that the theta hat direction is divided by the magnitude of omega r. And then we just have the stuff that's multiplying our operators, omega minus omega naught. So we can rewrite e to the minus I h t as being the exponent of minus I omega r t over 2. And then we have this dot product term. So we'll have minus gamma b sigma x over 2, no, not over 2, over omega r. And then plus omega minus omega naught. Omega r sigma z. And then, as you know, you can turn that into a cosine and a sine. So we'll have cosine of omega r t over 2 minus I sine omega r t over 2 times the dot product. So minus gamma b sigma x over omega r plus omega minus omega naught over omega r times sigma z is the same thing as our time propagator. So now, rewriting the time-dependent state equation in matrix notation, we can write it as being e to the I omega t over 2, 0, 0, e to the minus I omega t over 2. It's multiplied by sc, so it's that. We can write our time operator, which we just turned into a rotation. We're going to write it in matrix notation. So we're going to have cosine omega rt over 2 minus I sine omega rt over 2, and that's multiplied by omega minus omega naught over omega r. That's the first diagonal term. We have an off-diagonal term because we have it multiplying by sigma x, so we have omega rt over 2 gamma b omega r. Our other diagonal term will be cosine omega rt over 2 plus I sine omega rt over 2. It's just kind of flipped the sign on the I as per usual. And then this guy up here now is just, this is multiplied by sigma x, so it's the same as the other off diagonal. Thusly, okay. Right, and that is, of course, multiplying by the initial state vector of 1, 0. So now just doing a little bit of matrix multiplication. It's not psi of r, it's psi. Gonna keep the first term. Gonna keep it a buck with you. Keeping the first term. Not doing multiple steps of matrix multiplication in one step. And then it's multiplying by 1, 0, so we'll just get the first diagonal term. Up top. And the first opt diagonal term on bottom. Yuck. And then now we can write it, we can multiply these two matrices together to get, it's actually not two matrices, it's a matrix times a column vector, but whatever. I am going to flip the sign on the I first of all, but that's okay because I'm also going to flip the sign on omega minus omega naught. So we'll have plus I sine omega rt over 2, and that's multiplied by omega naught minus omega over omega r. And that's going to be multiplied by e to the I omega t over 2. And then this guy, omega r t over 2, gamma b over omega r. Okay, so that is, oh wait, no, I forgot to multiply the e to the minus I omega t over 2. Yes, okay. That's looking like what Shankar put then. So that part of the proof is done, and as if this problem didn't have enough going on it, we now have to see what happens when omega is equal to omega naught. In that case, the time-dependent state vector, very simply, is just the cosine. We have omega naught t over 2. We have I gamma b over omega r sine omega r t over 2 to the minus I omega naught t over 2. And we're supposed to be comparing it to the normal vector in the spin up z basis, which is given by cosine theta over 2 e to the minus I phi over 2 I sine theta over 2 e to the I phi over 2. That's what that vector is. So just doing a little bit of analysis on comparing these two guys, they're the same if gamma b is equal to omega r, which is fine, because if you set omega equals omega naught, then you're not really in a rotating reference frame. You're just letting the particle spin around in a cycle. So that tracks. It's equal if omega rt is equal to theta, which also tracks. That's just kind of how the angle is defined, and it also tracks if the phi is equal to minus omega naught t. This one is a little bit weird to think about, but I mean, if you just treat phi as rotating in the opposite direction as theta, then I think it works out just fine, and these all kind of make sense to me. Whoops. Finally, we need to calculate the expectation value for the magnetic moment, which will be given by the time-dependent state vector multiplied by gamma sz psi. So I'm going to write our answer, our time-dependent state vector, in column notation. Taking the complex conjugate as well, so we'll have cosine omega rt over 2 times e to the plus I omega naught, not even omega naught, just omega, plus I omega t over 2. And that is actually minus I sine omega naught, omega r t over 2 times gamma naught, or omega naught over omega r, all multiplied by e to the minus I omega t over 2. Right. It was supposed to be plus here, so sorry about that. And then the other guy was minus I gamma b over omega r sine omega RT over 2, and then we had the e to the plus I omega t over 2. Yeah. Okay. That's just the first column vector. We're going to be multiplying that by SZ. So it's just going to be, or gamma SC, so H bar gamma over 2, and then it's just the poly Z. And then multiplying by the column vector, the same guy, which I am just going to copy down, which is this stuff here. That junk. Alright, we got some matrix multiplication ahead of us, to be sure. So pulling the H bar gamma over 2 out front, and just doing the poly matrix multiplied by the original column vector. So I'm just pulling the row vector down here for posterity. That is being multiplied by, this is going to be a gross looking little guy. It's pretty much just going to flip the signs on them. So this one is pretty much going to be the same cosine omega RT over 2 plus I sine omega RT over 2 multiplied by omega minus omega naught, or omega naught minus omega over omega R multiplied by e to the I gamma t over 2. And then this guy's sign gets flipped like that. Sine omega RT over 2 e to the minus gamma, e to the minus I omega t over 2. Lovely. Now we just take the inner product of these two vectors here. So h bar gamma over 2, and then we have big old multiplication of stuff. Cosine omega RT over 2 minus I sine omega RT over 2 times the omega naught minus omega over omega R. That is being multiplied by this guy, so cosine omega RT over 2 plus I sine omega RT over 2, and that is multiplying by this fraction, omega naught minus omega over omega R. And all of that, multiplying the two second components of both of those vectors is just gamma squared b squared over omega R squared sine squared omega RT over 2. Okay. Big multiplications. Simplifying it, so actually expanding the multiplications, we have cosine squared omega RT over 2. We have sine squared omega RT over 2. And it's multiplied by omega naught minus omega over omega R squared. Right, minus gamma squared b squared over omega R squared sine squared omega RT over 2. So it's the same. Okay. We can simplify that, pulling together the sine functions. So I'm not going to do anything too crazy here. I'm just going to say plus sine squared omega RT over 2 times this junk in here, which is going to be omega naught minus omega over omega R squared minus gamma squared b squared over omega R squared. Double brackets. Okay. And then now, possibly the most dubious part of this question, noting that the omega r is just going to be the difference of omega minus omega naught squared plus gamma squared b squared. Just kind of a classical interpretation of the magnetic fields there. We will have that if we factor out an omega r squared, bracket parentheses bracket omega naught, omega minus omega naught, oh my goodness, omega minus omega naught squared plus gamma squared b squared parentheses cosine squared omega rt over 2 plus parentheses bracket actually, yeah, no, that's fine. Omega naught minus omega squared minus gamma squared b squared. That's multiplied by sine squared omega rt over 2. Okay. And that's on big parentheses. No, it's on big bracket. Okay. We have pretty much some trig identities to work through now, because we have cosine squared and sine squared additively multiplied by the same thing, and cosine squared and sine squared subtractively multiplied by the same thing. So we can group them together like that, where we're now grouping together cosine squared omega rt over 2 plus sine squared omega rt over 2. Both of those are being multiplied by omega minus omega naught squared. And then we have the gamma squared b squared stuff multiplied by the difference between these squared trig functions. And then using the same, or actually different trig functions as before. This identity is 1. This identity is just 2 times cosine of 2. Actually, no, it's just cosine 2 theta. So that's just going to be cosine omega r. Okay, cosine omega r. Finally, we'll have h bar gamma over 2 omega r squared. We'll have omega minus omega naught squared, and then gamma squared b squared. That was going to be cosine omega rt. Noting that the ratio h bar gamma over 2 is equal to the initial magnetic moment of our particle, then we can write the prefactor as being mu z of 0, and then expand the omega r squared again, and we define that to be just omega naught minus omega squared plus gamma squared b squared. And that is equation 14.4.31 from Shankar, so it's good. Yeah, long problem.